Okay, today we're going to be talking about bivariate data, and our guides for this is going to be looking at income versus food access. And we're using our favorite store in Texas, HEB. Okay, so bivariate data is data that has two variables. Bi, of course, means two. And two quantitative variables are visualized in a scatter plot. Now, scatter plots are something probably new to us. There is a way we can generate these on the calculator, and I will get into how to do that, but not right now. And so here we've got our data. We've got zip code, grocery store location, average household income, and the number of organic vegetables offered. Okay. And this is from San Antonio. We could probably do the same thing here if we wanted, but we're going to go ahead and use their data since they've already pulled it. Now we have two types of variables. When we were in algebra or pre-cal, we talked about independent and dependent variables. In stats, we call them the explanatory variable and the response variable. The explanatory variable is going to be the x variable, and it is the one that we are changing to see what happens to the response variable. And the response variable is always what you're measuring. This is it is the y variable. In this example, which one would be our explanatory variable? And in this case, it's going to be household income. So household income. And it's because we're investigating how well the household income predicts or relates to the measured outcome, the number of organic vegetables offered. Okay, and then our response variable is obviously going to be the amount of organic vegetables offered. And it's the outcome that we're measuring. And we think it's based on the average household income in that area. And we want to see how well these correlate. So let's take a look and talk about what correlation means. Let me pull this up a little bit more. Okay, so scatter plots. We have our explanatory variable on the x-axis. The y-axis is the response variable. And there are three different ways we can look at this. Positive correlation means that there's a positive slope, basically, if there's a linear connection or a correlation here. So this looks like a perfect straight line. We would call that a perfect positive correlation because there's a positive slope. Strong positive correlation means the points generally are all going the same direction, and you could put a line through them. Weak positive, again, there's a general upward trend here, but the points are pretty far away from any line you could draw through them. No correlation at all is I don't have any idea how to draw a line here and have the points close to it. And then we go the opposite. We've got a weak negative correlation, a strong negative, and a perfect negative correlation. They're all in a perfect straight line. So correlation measures how two variables are related. A positive correlation is that as the x values increase, the y values also tend to increase. It's just the same as the slope of a line. Negative correlations are as the x value increases, the y values tend to decrease. In terms of down here, you can see we've drawn in the line, the best fitting line that we could to get those points. And the least squares regression line is the straight line that roughly puts half of your data above it and half below it. So if I were to look right here, half my points are above the line, half are below. Same thing here in all of these. A strong correlation is when data is close to the least squares regression line. And those initials just stand for least squares regression line. In this case, the least squares regression line is a good model for the data. I could use the least squares regression line to predict new data. You would make close predictions. They would be fairly accurate. Predictions. There's no A there, predictions. If we have a weak correlation, data is far from the least squares regression line, and the least squares regression line is a meh, it's okay. It's just a so-so model. If you use that least squares regression line to predict some new values, you would be quite a bit off. It's not going to give you accurate predictions. If I were coming back to look at my HEB data, and so now I've got my explanatory variable of household income along the x-axis, the number of organic vegetables offered by the local HEB. And if we looked at this, the direction is definitely positive. It's going upward, so it's positive. In other words, as household income increases, the number of organic veggies increases also. In terms of the strength, so if we look back up here, here's perfect positive, all the points are on a line, moderate or to strong, and weak positive. If I were to try and draw a line in here, I could it's probably easier if I do it like this. I'd say it's moderately strong in terms of the strength, so moderately strong. And notice we are using that ly word again to modify our adjective here, moderately strong. We're not committing completely here. We're just saying it's moderate. Okay, and whenever we have bivariate data in a scatter plot like this, we're trying to describe multiple things. We first of all have to make sure we're doing things in context. We have to tell the direction. Is it positive or negative? We would want to see if there's any outliers, and we'll talk about that in a little bit. We need to talk about the form. Does it look like a linear model would be good or a nonlinear model? And typically the nonlinear model would be something more like a quadratic or an exponential. But we don't even have to say specifically. We just say nonlinear or linear. And then the strength, strong, moderate, or weak. So if we want to put this all together, I'm going to tell you that this is moderately strong. And I would say, putting it into words, the relationship between, I'm just going to use one I've already written out, the relationship between the average household income and the number of organic vegetables offered at the local grocery store appears to be linear. So there's my form. Positive, so there's the direction, and moderately strong, so there's my strength. There do not appear to be any outliers, because most of the points are pretty close to that line. And if I were to continue down here, we've got what we call a correlation coefficient. And this is a little r is the value. R can range from -1 to +1. +1 is when it's a positive correlation and every point is on the line. This would be a 0.91, so it's a little less than 1. We come down to 0.48 when it's weak positive. No correlation has a correlation value of 0. And then as we move into negatives, you can see the different R values here. And again, the only values are from +1 to -1. The strength, if R is close to 0, it means it's a weak correlation. If R is close to +1 or -1, it's a stronger correlation. Negative R values tell you have a negative correlation, so like one of these three. Positive R value is a positive correlation. And just because it's negative, it still can be perfect. So don't think that because it's negative, it's a weak correlation. Those don't have to go hand in hand. Okay, let's take a look at talking about some other things and some little difficulties we can run into. So if we were talking about average temperature at the beach, the amount of ice cream sold at the beach shop, and the amount of drownings. So we want to see what is connected here. And if I say that the average temperature during the summer is my explanatory variable, and the total amount of ice cream sold is the response variable, Here's what my data would look like. And if I had to describe this, I would say that the relationship between average temperature during the summer and total amount of ice cream sold at the beach shop appears to be linear, positive, and strong, I think. There do not appear to be any outliers. And second, does this relationship make sense? And yeah, I think it does, because if it's hotter, people are going to be buying more ice cream. So that makes sense. But what if I looked at something else here? What if I said, I want my explanatory variable to be the amount of ice cream sold at the beach, and I want my response variable to be the amount of drownings at the beach? Look at this. If I had to describe this, the relationship between the total ice cream sold and the number of drownings appears to be linear, positive, and moderately strong. There don't appear to be any outliers. But does it make sense? Does the amount of ice cream sold predict the number of drownings? No, because ice cream doesn't cause drownings. There must be something else going on here. And this is what we have to be very careful of. Just because you see a strong correlation doesn't mean that this causes this. Your explanatory does not cause it. Correlation only tells you that things are related, not that they cause each other. And the underlying variable in this case is the temperature. When it's warmer, there's more people at the beach, thus there are more drownings. So be very, very careful. Correlation does not equal causation. And the last thing, does ice cream really cause drownings? Absolutely not. But what's really going on here is that there was an underlying third variable, temperature, that causes the ice cream sales and drownings to coincide in terms of whether they increase or decrease. So we have to be very careful as statisticians not to assume causation when there could be something else going on. So ice cream sales and drownings are correlated, and they're strongly correlated, but they do not cause one another. Okay? This is huge. Correlation does not equal causation. So sometimes correlations have an underlying cause, a third variable. Correlations cause one another, but not in an assumed direction, and are completely random with no apparent cause. So here's some examples. Look at these strange graphs that we managed to find for you. So here we're graphing as an explanatory variable the number of movies Nicolas Cage appeared in and the number of people who drowned by falling into a pool. They're very closely correlated, but it makes absolutely no sense. The number of movies he appears in does not cause people to drown, right? How about this one? We've got the margarine consumed and divorce rate in Maine. Look at how closely those correlate. But they don't cause each other. There's got to be something else going on that's causing both these things to happen. If we look at this one, our crude oil imports versus chicken consumed, look at how closely these things go together. But again, they don't cause each other. They just are closely correlated. So there's got to be a third or fourth underlying variable that causes these. And finally, the number of letters in the winning word of the National Spelling Bee versus the number of people killed by venomous spiders. Look at how closely these correlate to each other. They go hand in hand. Yet we know that the number of words in a spelling bee in the winning word does not cause the number of people to get killed by spiders. These are just silly things, but happen to correlate with each other. They do not cause each other. Okay, so again, the important things to know, correlation does not equal causation. And when we are talking about our bivariate data, there are things we have to mention. We have to talk about the context. So anytime we're talking about data, we keep it in context. We need to talk about the direction. Is it positive or negative? What form it has, and the strength of the correlation. And then mention if there are outliers or not. Okay, that's it for section 3.1.